Hello again to another electricity lesson. We're looking at resistance in this lesson, and it's actually a very important lesson and something that I hope you are going to understand by the time I finish with it. And it's really fascinating. So the thing about resistance is that we looked in the previous video, the relationship between the current is that the current is equal to the voltage divided by the resistance. So if I were to look at a diagram, so this is a simple diagram. What we have is we have a battery here, a collection of cells. There's the positive end, the negative end. Electrons start flowing in this direction. As they're coming out here, they have a certain voltage. So as we get here, the difference of the energy that the electrons have at this point, or a coulomb of electrons have at this point and this point, is literally the amount of energy that the battery is giving each coulomb. So this is literally the total energy that a coulomb of electrons have to spend. Now when it comes into the circuit, it will pick up that there's only one resistor where they need to spend their energy. In this case, you can see there's no other resistor, but because there's only one resistor, they can spend all of the energy. So if this is a voltmeter, and this voltmeter takes the energy at this point and subtract the energy at that point, in other words, it sees how much energy is spent on this resistor, and all of the energy will be spent because there's no other resistor in the circuit. So in this case, my voltmeter reading at 1 will be equal to my voltmeter reading at 2. Now how will I get my current reading at this point? Now again, you can see the current never splits up. So my current at this point, and my current inside the resistor, and my current just before I go back into my battery, and my current just as I come out of my battery, everywhere the current would be the same. And I will get it literally at this point by saying that since my current here would be, I would call it the total current. It is the current that would come out at that point as well. Okay, now whenever you are in the main branch of the circuit, in other words, whenever you are measuring the current, and that current at that point would be the same as the current that just comes out here, we'll call that the total current. Now the total current will always be equal to the total voltage, which is the voltage over the battery. In this case, it's also the voltage over the voltmeter, because that's the only resistor in that circuit, divided by the total resistance. But now you'll see that the total resistance at this point is the only resistor. So if this is resistor 1, then the total resistance is equal at that point. Now let's look what is going to happen if we add another resistor in here. Okay, so we'll add another resistor. Here it goes. And this one will now be called R2, resistor 2. And now all of a sudden, the amount of energy I spend at this point cannot be equal to the amount of energy that I spend at this point. So sorry, I mean the amount of energy that I spend on the first resistor cannot be the total energy of the battery, because then I will have no energy left to spend at the second resistor. So notice now that that this time the voltmeter reading, the total voltmeter reading, would be equal to the voltmeter at this point plus the voltmeter at the second point. The total resistance, let's do resistance in green. The total resistance is now simply, well, there's now two resistors. Okay, it is in the same main branch, so my two resistors will now be resistance 1 plus resistance 2. Okay, and now what will my current be equal to? Okay, my total current, I've been doing current in blue, my total current would be equal to my total voltage divided by my total resistance. Okay, so now if I wanted to measure it here, I would have to take it like this. I would have to take my total voltage, which is the voltage over the battery, divided by my total resistance, which is simply adding these two, and that will give me, again, at any point in here where I measure the current, it would be the same. But let's say, for example, I did not have the voltmeter over the battery. I only had the voltmeter over resistor 1. Okay. Now, if I only had the voltmeter for resistance 1, I would use the same relationship, but I would only be able to measure the current that comes out of resistor 1 and that goes into resistor 1, since the current that goes in goes out must be equal. So in other words, if I only had the voltmeter for reading 1, I would say, well, the current in resistor 1 is equal to the voltage over resistor 1, the potential difference, divided by the resistance of resistor 1. And let's say the question then asked me, well, what would be the voltage over voltmeter 2? So now I need to calculate the voltage that I can read over resistance 2. And so I can do that by looking at, okay, I know that the current in resistor 2 will be equal to the voltage of resistance 2 divided by the value of resistance 2. And so if I multiply both sides with R2, I will get that voltmeter reading, the second voltmeter reading would be equal to the current in voltmeter 2 times the resistance of voltmeter 2. Now, say I have the resistance, where am I going to get the current? Now, this is where it becomes important to understand what series means. Series means when resistors are in series, it means the current does not split. The current that goes into this resistor 1 is equal to the current that goes into resistance 2. So if I worked out the resistance because I had the voltmeter reading on 1, I could work out the current in resistor 1, and therefore I can work out the current that goes into, because again, current in a series is everywhere the same. Okay, so here I can then go and work out what is voltmeter reading 2 by getting this one from, so I get I2 because I1 is equal to I2. The current in resistor 1 is equal to the current in resistor 2. And then voltmeter reading 2. Now I've got voltmeter reading 1 and 2, and I can use that to get the total voltage for the system. Okay, because those are the only two resistors. Now if I add one more resistor, it would just work exactly the same. In other words, adding one more resistor here would have the effect of, so this is resistor 3, and now my total resistance would simply be plus, let's move up a little bit, plus R3. So if I wanted to get the total current, the current at any point in here, the total current, all I'll have to do is keep in mind that the resistor here at the bottom must be R1 plus R2 plus R3. Okay, and the voltage at the top must either be the voltage over the battery, which is the total voltage, or it must be the voltage over each of them added together, voltage 1 plus voltage 2 plus voltage 3. Now what I do want to show you something is that when we add resistors in series, okay, so what is the effect of adding resistors in series? And this is quite important. When we add resistors in series, the total resistance increases. Total resistance of the system increases. What do I mean by total resistance? Well, it means that as the voltage over each system would decrease. So, and the reason because when there was just the one resistor, I could spend all of my energy in that resistor. When there's two, I have to share it proportionately. So I'll give more energy to the resistor that requires more energy. The higher resistor will take more energy. And that increase in resistance reduces the current that can flow. So if I add another resistor, 3 resistors now again I'm increasing the resistance. Now when I increase resistance, remember, current is inversely proportionate. Okay, inversely proportionate, which means that an increase in resistor will in total resistance will decrease current, and that is, it will decrease the total current. Now an increase in total in adding resistors in series will increase the total resistance that is experienced in the circuit, decrease the total current, but voltage, the total voltage, will stay the same. The total voltage is literally the amount of energy that the battery gives the each coulomb of electrons. So an increase in resistance, even though it decreases the current, it doesn't affect the total voltage. That stays the same. It does affect the individual voltages, because each resistor now uses a part of that energy for themselves. So hopefully that makes sense, but this is very important just for understanding. Adding resistors in series increases total resistance, therefore decreases the total current, although voltage stays the same. Well, in the next video we'll look at adding resistors in parallel. In other words, what would happen if I now, instead of having added this resistor like that, what would happen if I add a resistor along here? Sure. If I added a resistor here, does it still have the same effect? Well, you'd think so, but it doesn't. We'll look at that in the next video. Thanks for watching.